Thanks. So actually, a better title would have been random walk by isometries on the Euclidean space. So I'm considering, let's first of all start with the most important thing, that is a joint work with Peter Varju from Cambridge University. And the starting point, we're considering the following random walk. So consider a random walk on d-dimensional Euclidean space. Very simple. I mean, I'm just taking xi is a random variable with values in the isometry group of Rd, and not that it makes much of a difference, but I prefer to take the orientation preserving part. So this is SOD semi-direct product Rd. And for simplicity, though this is nowhere needed, let's assume it has finitely many values. What you actually need is some moment assumption, and for everything I say to be literally true, you need force moments, and with slightly less weaker exponents, you could take anything which is more than 2 moments. And then I am looking at some point, some fixed point P0. So P0 is some fixed point in Rd, and I'm applying first the first random isometry, then the second random isometry, up to the nth random isometry. So of course the special case is the usual random walk on Rd, where the isometry I'm taking is just translation. That's a special case. I'm not going to say anything new about the standard random walk, so let's make an assumption. So I'll make an assumption, assume throughout my talk that if I take the set of values that xi attains, all of these xi's I forgot to say, they are identically independent, identically distributed. That if I take the group of the isometries which I actually see, I take the groups that they generate, I assume that it is dense in this group G, which, if you wish, implies, so let me just make some kind of notation. So this is probably a nice place for my notation. If X is an isometry, there's a well-defined projection from the isometry group of isometries to just the rotation part. So theta X is going to be the rotation part. This is inside SOD. And less canonical, I'm going to take the translation part, which is just by definition what my isometry does to the vector 0. Okay, so my isometry basically is defined by x goes to little x goes to theta of little x plus little v. Okay, so that's somehow notation that I would use throughout. So this assumption that the support is dense is basically the same thing as saying that if I just look at the theta part, at the rotation part, it spans the dense subgroup in SOD, and in addition, no common fixed point for all of these xi in Rd. So that's my assumption. So let's see for a minute what let's try to see for a minute what is this what happens if I do this? Let's just sort of do it. So, no symmetry. That's my assumptions. Notice that why did I somehow... So let's look for a minute at what this actually is. So I start with some point P0, and I have here, so this would be actually a sum. So each time I rotate plus translate. So one term would be that I rotate according to maybe just to save some chalk, I'll write the rotation part of the nth term as theta n and the translation part as Vn. So one term is I take the rotation of P0 by all of these rotation parts. But another term I sort of just before the last step at the first step I took P0 to be theta 1 P0 plus V1. So then I also have here this V1 would also be rotated, but not by the first rotation because it sort of just appeared after I applied the first rotation. And then there will be, well, you can see, then there would be only the last rotation applied to the n-1th translation, then there's the nth translation. So, okay, there's this sum which is a bit different. Basically, either with it or you have here this part here. This is the sum of capital N random variables, which are which is somehow each of size which is fixed. Now they're of course not independent, which is somehow the key point of the talk. If I know what the nth translation is, I quite likely know actually what the nth rotation is, so there's some kind of information I know about this sum. There's certainly, so Sn, this Sn is the sum of, okay, one term which I can more or less safely ignore, the rotation of some rotation, random rotation of my original vector, plus n, capital N, bounded, in our case, random variables. And so the key is that they're not independent. Now, let me state what Varju and I proved about these random walks. And then, so our work was based on earlier work which Varju did by himself. I would also explain what Varju did by himself, which is in some sense lesser than the theorem, but in other senses greater. So you would see. Xi's are like here. We say so xi as before. Xi in the isometry group, right, are valued in isom ℝd valued random variables as above. Technically, I guess it's to the left or right, but depending on your own orientation. And I'm going to make an assumption, a big assumption, which, okay, the truth is I'm saying it's a big assumption, but possibly it actually is satisfied automatically. assume that the rotation part, if I look at this, the rotation part has the spectral gap property. I'll explain what I mean that. I'll explain what I mean in a second, but I guess here people, even without me explaining what it means, know what I mean. This will actually contain some information, not when they act on the sphere, but actually on the L2 of the group, which is slightly stronger. Now I'm going to take this just notation. Z is just this ordinary standard Gaussian random variable. So it's maybe not a surprise that I would relate a sum of n random variables to a Gaussian, and there would be some standard deviation. There would be some standard deviation sigma, and there would be some vector p. I should have called that one. So okay, it's called q0. It's a vector in RD, and now the statement is that, and I'm going to take some smooth test function f, and finally I can tell you what we prove. I take the conditional expectation of f after n steps of this random walk, what I called S capital N. I compare it to the expected value of f under this standard Gaussian rescaled by something which is proportional to what it should, to square root of the number of summands in this sum above. And I need to recenter this possibly. So I have here the actual random walk distribution. I'm comparing it to a standard Gaussian distribution. And the difference is bounded by some errors. So what are the errors? It will be bounded by some constant depending on p. And L1 norm of f.
You know what sigma things that you say
Exist, yeah. They are somehow.
You know how to compute them in terms of this.
Yeah, more or less Q naught is the point which is least moved by all of these. Yeah, it's somehow. Yeah, there's not much mystery there, but. And here's an error rate, e to the minus some constant, and some Sobolev norm of f. So the Sobolev, basically I'm asking for d plus 1 over 2 derivatives. Yeah, what was the question? P0, this starting point. It's basically, yeah, I mean, it's something very explicit. Basically, the norm of P0 or something. But I mean, I can't, if I take P0, which is dominates the whole sum, I can't expect any kind of distribution. So this is some kind of, this is sort of a standard type of bound. This error term is basically related to what's called the Berry a scene bound. It's sort of related to that. Basically, little c depends on the spectral gap. Yeah, or, in fact, on all of the data. So c depends on the so little c depends on the spectral gap, and also on the translation part in a weak way. I mean, again, basically on how the second moment and the third moment of the translation part move. So little c also depends on the random walk. Again, not in a very dramatic. I mean, sort of the most. This we don't give explicitly because the way we use the spectral gap, we sort of put it into a big machinery. So I don't give you this. This constant is explicit. This c, in theory, somebody who's masochistic enough could make it explicit, but that's not going to be particularly pleasant. But sort of the interesting, so this is a polynomial. This is a polynomial error, and that's sort of basically what you could expect. I mean, somehow it's not. You can't expect more than that in a Gaussian distribution. But this error term is actually the more interesting one, and the one with some novelty, because you see that it's exponentially small. So you're allowed to take. So this means that you're allowed to take. Somehow f, which is concentrated with, let's say, L1 on 1 to normalize things, concentrated on exponentially small balls. Yes, but it doesn't depend on capital N.
Yes, but if I just multiply it by 2, then the second term is not needed.
Depending on what f is. That's somehow the key point here, that you could allow. I mean, if you just fix an f and forget about it, there's nothing interesting. But I'm taking f which are very wild. I'm taking f which are concentrated on a exponentially small portion of space.
You could get a small set, for example.
Yeah, so this f, this is somehow, this statement has all of the dependence on f. So I'm not fixing a test function f, that's an important point. I can take, for any capital N, I choose a test function f which sort of exploits this bound through the limit. And so what this bound does not say, it does not say that this distribution approximates Gaussian exponentially well. But what it does say is that this distribution approximates a Gaussian distribution even if you probe it up to resolution of exponentially good resolution. So somehow if somebody in his computer program would like to generate a random Gaussian, that would not be a completely bad way to do it. It's sort of you get some random bits and then you get a Gaussian up to a scale which is exponentially small. Of course, simulating a random Gaussian is not so hard from the computer science perspective in any case. But anyway, that's what this statement gives.
But the function f, can it grow?
The best is to think of this function f as having, you think of it as having L1 norm 1, okay? And then the question is how wild can it be? How much can it fluctuate from point to point?
One way to use it would be to capture, to hit a very small set, right?
Yeah, that's sort of, so a corollary, let me state a corollary of this, just to somehow corollary, which would play a role later, but let me just state one corollary of this, a trivial corollary, very special corollary that there will be for appropriate little c small, maybe different, let's call it c prime, which is small, and big C, which is really big. If I would take the probability somehow uniformly on, let's say, y, I look at the probability that this random walk xn up to x1 times this point p0 is in a ball around y of exponentially a small size, let's say exponentially with a capital E, with a big constant, this probability is exponentially small. And again, there's an implicit dependency on the beginning point, etc. Okay, so that's sort of in particular, that's one corollary of this theorem. Of course, the theorem says much more. Let me say one thing, so maybe I'll erase this here and let me tell you before that. I told you that we built on previous work of Varju, so let me tell you what was existed in the previous work of by Varju by himself. So Varju. And here it's important there's no spectral gap assumption. So it's completely for any rotations which span a dense set, and you look at this difference, same difference between my random walk by isometries and the Gaussian distribution. It's again, there is the same polynomial dependence and stretch exponential dependence on the same Sobolev norm. So it's not as strong because it only probes up to a scale which is not exponential but a stretch exponential. On the other hand, it's stronger because there's no spectral gap assumption. If you add into Varju's proof a spectral gap assumption, it improves, but does not improve all the way there. So if Varju would have assumed spectral gap assumption, then this 1/4 would have been 1/2.
Why is a corollary just an upper bound? If the probability of hitting a set is something explicit?
Yes, absolutely. But I was thinking ahead of what I want to say in a few. You're absolutely right, but there was a reason I did it this way. There is a history to this problem. This problem was not born today. It was somehow studied at least since late 60s. So a central limit theorem, which of course this implies, but in a quantitative way, a central limit theorem in this context is due to Bourgain from 67. And the truth of the matter is, I told you that this theorem in particular is a central limit theorem, but somehow the central limit theorem part, which corresponds, I mean, when you prove a central limit theorem, one of the ways is to look at the Fourier transform. The central limit part, the part where you see the Gaussian, corresponds to the low frequencies. For the low frequencies, we just use essentially Bourgain's method. So that somehow it's not, so this work is not superseded, but actually used in what we do. The local limit theorem just says that if you take a fixed, like Professor Sinai wanted, you take a fixed test function f, you want to have these things. Well, if you take a fixed test function f, because the Gaussian becomes wider and wider, you need to rescale everything by this n to the d over 2, just to make sure, right? I mean, for a fixed test function f, if you have a Gaussian has in every dimension has weight square root of n. So you sort of expect that both of these terms will decay like n to the minus d over 2. So just somehow the local limit theorem for a fixed test function after you normalize by the appropriate constant. This was also considered in the 60s. So for d equals 2 was proved by Kashdan and Givarsh around the same time. Basically, yeah, I don't want to give a precise date, but around the same time. For general D was actually a well-known, or fairly well-known was sort of an open problem until Varju solved it for D greater than 2. What I should also say is that independently of Varju, and I think probably I think actually posted before Varju posted his works with the spectral gap assumption. But not in a quantitative way. The local limit theorem was proved by Konz and Givarsh around the same time as Varju proved his theorem, posted a bit earlier, around the same time as Varju. So this was somehow open for whatever, 40, 50 years, whatever.
D equals 2, the fact that the rotation gives a billion. Why would you be able to do D equals 2 and not higher?
Because the rotation group is a billion. I mean, for D equals 3, you have a serious group, and yeah, no, that's somehow for D equals 2 is somehow much. It's a very different case.
So there's two elements in here. One is this exponential error that you get, and the other is the fact that you've got this correlation among the entries that you
Yeah.
describe. So are these two independent issues, or are they connected?
No, I mean they are connected. If you take an ordinary random walk, independent, a perfect random walk, then because there's only, so if there are only finitely, let's say 100 values that xi can have, you'd have at most capital N to the 100 possible options. So if you probe at a scale smaller than n to the minus 100, you're going to get jumps. So it's not somehow that we are somehow get rid of these correlations and then prove it. Actually, I mean, without this correlation, nothing this strong would be true.
Okay.
The correlation, instead of being something that works against you, helps you in a dramatic way.
No, I understand that. I just want to be sure. Yeah.
So just let me be precise what I mean by this spectral gap assumption, since everything hinges on it. I should say, I mean, it's sort of essentially automatic, because I assume that there are only the support of the random variable is finite. But okay, if you actually were a lawyer and took everything that I said, that somehow you could switch to continuous random variable, etc., this theorem is only true for D at least 3. But as Peter mentioned, the isometry group for D equals 2 is a solvable group, sort of not very frightening group. The isometry group for 3 dimensions and higher, that's sort of a serious group, and that brings this, the fact that it's a serious group brings into, yeah, it somehow makes life very different, as we know. So the spectral gap assumption, let me spell it out in detail. So one way to say it, I define an operator on functions. So this is an operator on L2 of SOD, which takes a function, and let's say I want to evaluate it at the point x in the group. Its expected value of f, where I apply the rotation part of my random variable. So this is an operator from L2 to L2, not necessarily self-adjoint, because I haven't assumed, like Doron pointed out, I haven't assumed that my random walk is symmetric. So basically, so basically what I want to assume is that there is some k, so that the norm, and probably you could say, I mean, probably this k is enough to take it to be 2 or something, but doesn't really matter for me. So that if I take this operator and restrict it to functions which are orthogonal to the constant, because the constant I could shift it until I'm blue in the face and average, I'm not going to get anything else. But any other function you could expect to have some decay would have norm less than 1. So this is very, right, a very strange, this is sort of very strong condition that you have, that no matter how wild your function is, your norm, the norm after you apply the operator decays by a fixed quantity. That's something which does not happen for d equals 2. This is sort of so surprising that just the existence of such operators resolved the Rusevich problem about invariant means. So this is somehow, I think this is really the fact that there exists such t is a highly non-trivial, highly surprising at first view fact. Equivalently, maybe somehow equivalently, more explicitly, the Kashdan is, yeah, Kashdan is the Kashdan that.
So what's funny is that he only did the d equals 2 case where he couldn't use his property t. So it's kind of
yeah, I mean, I think this is probably even predates his property t paper, which means that it's quite ancient. No, but Kashdan is the Kashdan. So, and Guvarch is also somehow, right, a serious person in the field. These are not. Equivalently, if theta 1 up to theta r are the possible values for possible values of the rotation part of one of my isometries, they're all identically distributed. Then if I take a self-adjoint operator by 1 over 2r summation I from 1 to r, f composed with theta I plus f composed with the inverse. Now I have a self-adjoint operator, so I just wanted this operator on the complement of the constants would have norm less than 1. Okay, so that's equivalent. So, okay, I mean, this is the fact that there are such operators is both surprising and deep, and in fact was first shown using Kashdan's property T by, I believe, by Margulis and Sullivan for high dimensions, and later by, if I'm not mistaken, Drinfeld for dimension for d equals 3 and 4. There's a beautiful example by Lubotsky, Phillips and Sarnak of such rotations, which builds upon deep deep work of Delin. that if you take, so you take sort of x, y, and z axis, and you rotate around them by something like arc cosine 3/5, or maybe it's arc cosine 4/5, one of the two. You rotate by this particular degree, either clockwise or counterclockwise, each one of the coordinates. This gives you three rotations and their inverses. Then you get a spectral gap. For this example, so this is Lubotsky-Philip. This is Lubotsky-Philip-Sarnak, which sort of basically builds on a proof of the Ramanujan conjecture by Deligne, is that the spectral gap in this case is something very explicit, square root of 5/3. So, okay, so there are cases where it's actually, well, there's pretty handsome, one can say, optimal spectral gap. But I mean, if you're not so precise, there's actually, you could construct such a collection of rotations very easily. So there's the theorem of Bourgain and Gamburd, which basically says if these matrices, these are rotation matrices, the generated dense, they are given inside SO3, are given by by matrices with algebraic entries. The entries are algebraic numbers. Already, you could just, if you want, take them to be given by rational numbers, but then algebraic entries, and span a dense subgroup. Then the corresponding operator has a spectral gap. Then have the spectral gap property. And this was extended, so this is sort of highly, SO3 and SU2 are for my purposes the same group. So, okay, though somehow some people might object to that heavily. But for these purposes, because somehow just index 2 issue, they're the same group. So then Bourgain and Gamburd also generalize it to SUD, general D. This is actually, this is far from being a root. I mean, this is sort of requires some heavy duty work to do this. This is still Bourgain and Gamburd. And actually very recently, the Sachs and Benoit, probably I should have did it the opposite way, Benoit and the Sachs, proved this statement for a general for any compact, simple, real algebraic group.
They're using the same, this requires initially the local ring conjecture. They're using all those tools.
They are using all those tools. I mean, it's somehow, I think it's fair to say that they're taking the Bourgain-Gamburd proof. They're sort of conceptualizing it a bit. They're cleaning it. They're identifying the components, and then they are able to extend it. It's sort of the versions of the sum product theorem, etc., that you need are all contained here. But this is not. This is also not a routine extension. It requires understanding some things. Okay, so that's good. Our theorem is not vacuous. There are rotations with the spectral gap property for any d, and actually it's not so hard to write them down. Now, how does the proof actually go? Let's see which board I'm willing to sacrifice. Well, as I said, it goes through Fourier transform, which is not a great surprise. And if you're taking Fourier transform of everything, then you get an action. So via Fourier transform, you get a new action. So obviously, the group of isometry of Rd acts in an obvious way on L2 of Rd. And you could intertwine this with the Fourier transform. So after you do Fourier transform, you get a new action, which is of course equivalent to the old action, new action of the isometry group on L2 of Rd. But the action looks a bit different. So the action, so if I take G, apply it to a function f, take the Fourier transform at some xi in Rd, I get, where the rotation part acts like expected. Maybe there's an inverse somewhere, because I don't know. That's what happens when you act. You sort of have to have inverses, otherwise it's not going to be a nice action. And there is a phase, and I believe the phase is and of course here I'm using G is theta, the rotation part is theta, and the translation part G on 0 is V. I'll do that somehow. So the action somehow of the isometry group on Rd is sort of, mixes things around. The action on Fourier space immediately shows you that this representation is not irreducible, because you see that this representation acts on every sphere, sphere by sphere. Right? So this exercise basically told us that we are looking at that somehow this action is that the action of the isometry group on L2 of Rd is actually a direct integral of representations. So we established this, the action of the isometry group on L2 Rd as representation of the isometry group. After sort of taking a Fourier space, we wrote it as a direct integral of representations. Each HR is, you could think of it as being functions on a sphere with the action given by G of a function f at xi. Now xi is taken to be in the sphere is a phase. Now, because I'm sort of normalizing everything to be on the sphere, I need to explicitly put the size, somehow the parameter r, in the exponent, in the phase part. Okay, so I have here a one parameter family of representations. And the real theorems that Varju and I proved is not about random walks. What the real theorem that we proved, the thing which contains the whole content of the improvement over the previous result of Varju, is the following uniform spectral gap estimate. So this is a real theorem. The other theorem was also a real theorem. It's true, but it's somehow is a combination of what Varju proved by himself with what we did together, and this is what we did together. There's a uniform construction estimate. So if I have you could, for the spectral gap estimate, you could reduce to the case of symmetric of a symmetric set. So maybe S is so let's say I'll sort of switch notations a bit. S is inside the isometry group of RD, let's say symmetric, and then I have AS somehow the corresponding averaging operator. It's the averaging operator, maybe think of it as lying as working on this L2 of RD, but then you get an operator on each AR, and then you can look at the norm estimate of my averaging operator from this representation HR to itself, right? It sort of acts, the representation is reducible. This operator now works on each representation by itself. Now for R equals 0, this is just the averaging operator on the sphere. Averaging operator on the sphere has a spectral gap. That was part of my assumption. That's a weak form of my assumption. But there is a constant vector who has norm 1. So and here I'm sort of taking the whole space. So certainly this norm is going to be 1 when R is going to be 0. And it's continuous in the parameter R. So the best you could hope for is more or less what is this kind of estimate. So for every R bigger than R0, you get a uniform spectral gap. And the fact that you have to go near R equals 0, the fact that sort of the truth is that it's a spectral estimate is one, depends on R squared, that's somehow, that's certainly already in Tutubalin, etc. So I mean, somehow that's no surprise. So this is somehow a uniform. I mean, though strictly speaking, it's not uniform because of some well-understood problem when you approach R equals 0. I think it's still fair to say that this is a uniform spectral gap estimate. And the key is uniformity. So the key is the uniformity. The key is the uniformity. And I mentioned earlier Cons and Givarch. I'll mention them again. So without an estimate, or just so an ingredient in the proof of Cons and Givarch of this local limit theorem was actually a non-effective proof that the norm of this estimate for any R bigger than 0 is less than 1. This is Cons-Givarch. So somehow the key is uniformity, and in any case, uniformity is the only thing that is new here, because the fact that the spectral radius is less than 1 was proved by Cons and Givarch. Now, this uniform spectral gap estimate is a useful thing. I somehow counter this. I want to do two things. I know I won't have time for both, but I still want to I want to give another corollary of exactly the same. So it's a corollary of the same spectral gap estimate. And because I sort of write things in a very strong way, it actually also uses, it's a corollary of the spectral gap estimates plus a very clever idea of Miklos-Abert. So this plus some sort of nice lemma, cute lemma of Miklos-Abert gives the following theorem, which relates to things I was doing here as a postdoc with Schlag and Perez many years ago, motivated by discussions with Professor Sinai. So I have here, now take theta 1, theta r to be fixed rotations in SOD with spectral gap. In the sense that the averaging operator, when you take them, you take their inverses, has spectral gap. So I now define similarities. These are a collection of similarities, are sort of, for every I, this is a one parameter family of similarities. Okay, and VI are, I don't need to assume much, so VI are continuous. And I'll also assume that at 1 I have this collection SI1 have no common fixed point. Lambda is a parameter between 0 and 1 at the moment. 0 is not very interesting. And I have my theta, then I'm also going to take some fixed probability vector. So Pi is a fixed probability vector. Just a collection of positive real numbers. The sum is 1, and somehow taking one of these probabilities to be 0 counts as cheating, which is not allowed. Then for any k, ignore the k, take k equals 0 if you wish. Already interesting. There exists some lambda depending on k less than 1, such that if all of these, if I take lambda I, for every I take a lambda I in the interval between lambda k and 1, and if I take mu to be the self-similar measure corresponding to this data, so there's a unique probability measure satisfying, because my lambda are less than 1, that mu is the average of the sort of the measures I get by contracting by similarities. Okay, this defines uniquely a measure mu, self-similar measure. Many people love them. Then this measure is regular with Lebesgue, not just regular with Lebesgue. Here's where the k comes into the picture. The Radon-Nikodym derivative of this measure with respect to x is inside ck. Okay, so it's not just that I have a this measure, self-similar measure, is regular with respect to the Lebesgue measure, and it has k derivatives. And people who know Bernoulli convolutions, ℝdRd problem, this has a history, this kind of problems. This is, yeah, so one of the problems that I sort of worked on, I mean the problem that I worked here when I was a postdoc, still open, is understanding the Bernoulli convolutions. For Bernoulli convolutions, that is a dream. If you proved something like that, you'd actually prove Lemmer conjecture, this interesting case of Lemmer's conjecture for Bernoulli convolutions. So we don't prove Lemmer's conjecture. But what I'm saying here, that you ask an analogous question in 3 dimensions with putting in, sort of somehow putting in these rotations with a spectral gap, which are non-trivial, then you could solve it. Then you could actually show that you have as many derivatives as you want close to the bound. And so what's nice is that this theorem and the estimate on random walk on random It's a self-similar measure. Even Bernoulli convolution is better to think of as being as a self-similar measure. It's a self-similar under translation to the right and translation to the left. The right concept is that of self-similar measure. Okay, and there was actually an analog for one can have there's an analogous result to the spectral uniform spectral gap estimate for graphs over finite field.
Sort of allows you to now do, before you had just isometries and now you're scaling a little bit. This lambda k obviously depends on the spectral gap.
Yes, of course. And this would have been easier if I took the same contraction each time. If I took the same construction each time, then basically there would be some relation between the Fourier transform of my measure on some shell and the Fourier transform of my measure on some either bigger or smaller shell. We can figure it out later. And basically, just because of this, you would get some decay of Fourier transforms. The decay is fast enough, you get smoothness. That's the reduction. So somehow the reduction for constant contraction ratios to the spectral gap estimate is fairly straightforward. If you use different ones, you need to be a bit clever. Instead of being a bit clever, we took a ride on ℝdRd's lemma, who was clever for us. Okay, let me. I could present some other results, but I want to actually go back to this corollary. So I want to somehow talk a bit about the strategy of this proof in the 5 minutes that I have left or so. So this is for instance the Institute. Jean unfortunately is not here, but somehow it's his road that we were taking. The basic strategy. So we wanted to prove this. So the uniform spectral gap implies, essentially by Varju's work, implies sort of local center limit theorem up to exponential scale. Which implies this corollary on non-concentration, if you wish, that Peter complained is somehow too weak in some sense. It doesn't really capture. It doesn't capture the form. I mean, in fact, I know not just in upper band, I know asymptotically, with some reasonable error rates, how much mass there is inside these balls. Oh, I don't know. Anyway, certainly I know that. And now, and that's basically somehow the beautiful machines that Bourgain and Gamburd built is a way to pass from this type of non-concentration to a spectral gap estimate. So this, going from here to here, basically used the Bourgain-Gamburd machine, if you like, or Bourgain-Gamburd bootstrapping argument. It's not, you can't just take the argument out of the box and apply it. You have to somehow do a bit more, because I'm not sure. So this Bourgain-Gamburd argument, you start with some initial estimate, which here would rely heavily on this non-concentration estimate. You then do some additive combinatorics, and then there's some final grace which sort of push you at the end. And the final grace that pushes you over the end is a bit different, because this group that we are considering is not a compact group or a finite group, so sort of it's maybe infinite in a mild way, but it's certainly a non-compact group. So there's sort of some issues there. But the main thing is this non-concentration estimate, and somehow the way we prove the non-concentration estimate so the non-concentration estimate which we want in order to prove the spectral gap estimate, we prove using a weak spectral gap estimate, proved via weak spectral gap estimate. Which likely is sort of not very far from what Cons and Givarch did. The weak spectral gap estimate is the following. Let's call it proposition. There's some constant c depending on my generators, such that if I have two parameters which are close to each other, maybe large but close to each other, for at least one of them the bound on the norm is at least one of them I have some kind of effective bound on the norm. So basically the idea here is not so surprising. I mean, if there is, because of the spectral gap, if there is a bad vector which is not contracted by my operator to be unique, and if I have two parameters which are nearby, then these vectors which are unique have to be also close to each other. This all comes from the spectral gap. But because the phases change, I mean, they don't change dramatically. That's the reason why these constant functions have to be close. But because the phases change, they can't perfectly fit both of them. So you lose, at least for one of these radiuses, you lose something. So you have a weak spectral gap estimate. And then the non-concentration estimate amounts to, in the end, what it amounts to in the end, so the non-concentration estimate amounts to, if I have nu n is a distribution of xn minus 1, x1 times p0, right? This is the distribution of this random variable is a probability measure I call nu n. And basically what you need to prove is that when you convolve nu n with this reflected measure, the measure of a small ball, of a fixed ball around 0, of some small size, is going to be small. So I'm studying this measure, I look at its Fourier transform. And what I would love to have is to have some kind of decay of the Fourier transform of this measure. That would make me extremely happy. Forget for a moment that you know that the coefficients of this Fourier transform are all positive. Think of it just as a measure. Now, so I have here a measure, and basically what I want is to prove that the integral of the Fourier coefficients along a shell of radius r, for each r decays polynomially. That would make me exceedingly happy. And what the information I have from this weak spectral gap estimate, I don't know that, but I know that somehow basically in every kind of shell there could be there's at least one good guy. That's one way to put it in each shell. Now, Fourier transform of measures have some restrictions on them. I mean, they can't just be an arbitrary thing. So in particular, this measure you could decompose into a part which is very close to the origin and a part which is far away from the origin. The part which is not very close to the origin you're averaging. I remind you again that I'm averaging not the absolute value of the Fourier coefficient, just the Fourier transform of this measure. So the part which is far from the origin, when you average, worst case is a spherically symmetric thing, you could estimate it, decays polynomially. And the part which is on a very small ball, well, if you have a measure which is supported on a very small ball, the Fourier coefficients don't change so quickly. They have some they're Lifshitz with some small Lifshitz norm. So so there are parts which sort of decay polynomially because they come in this integral which comes from the part of the measure which is far from the origin, and there are parts which, because there's sort of one radius there, sort of is a testimony for the goodness of all of its neighbors. That somehow finishes very impressionistically that part of the proof. So thank you.